Should we just always use balanced accuracy? Or maybe F1 scores you want to always use? Note, in addition to many possible single number metrics, different cultures call the same thing by different names. And it's unclear just from the recipe standpoint. I won't be able to give you a recipe of, just very reassuringly use this and you'll always be right. Just, okay. For example, statisticians call the same things that we usually call in machine learning false positives. They call them type 1 error. And what we call false negatives, statisticians usually call type 2 error for historical reasons, I guess. And I believe now you will never forget what false positive is after this picture, right? Just kidding. So which metric is the right one? If you notice, there is a ton of metrics here that people use. And this is just a subset, actually, for information retrieval from Wikipedia. But there are many, many others for different other purposes. For ranking, we would use a different one. And some of the metrics are not here, for example, that mean, average precision, and average precision, and so on and so forth. But those metrics here, they are all based on our confusion matrix with positive, negative, and predicted as positive, predicted as negatives. All of them are based on the true positive, false positive, true negative, false negative. Okay. So confusion matrix is really nice, right? It does contain everything, all of the information, but it's very hard to use as a single number to say, oh, okay, look, my model is better than yours. Yours. Or for other purposes like that. So different metrics for different cases, and thanks to no free lunch theorems, and thanks to this situation with the metrics, you will never be out of job if you're smart and hardworking and grow into your field and understand what's going on, because you have to look at the problem all the time and decide every time you see a new problem. It is not just a simple recipe, oh, do this and it will be done. You have to understand the specific, you have to understand what your stakeholder, your customer wants, and what are they evaluating in their metrics, what your model will be doing when it be deployed, and all sorts of things. So all of those metrics are useful, but the answer to the question which metric is the right one is it depends, because metrics by themselves as single numbers, including accuracy, also are bad for the following reason. It's not, for example, in the case of accuracy, it's not bad just because it doesn't handle imbalances in the classes, but it also is bad because it doesn't take into account the decisions that will be made after the model that we chose as the best is deployed. What we need to take into account, not the decisions themselves, but the consequences of these decisions, their costs and their values, and then make our decision about which model is the best, depending on the costs and the values of downstream use of those models. One way to take those into account is expected value. Well, you already know expected value from probability theory, and we're using this all the time recently in JMM algorithm with expectation maximization. This is similar, the concept is similar. So let's denote an outcome I as outcome I, O sub I. And the probability of that outcome as probability of O sub I, surprise. And the value, now we're outside of machine learning, we're in the real world use case, and the value will be V of O sub I. And then the expected value is nothing but, as you must have already predicted, is just the sum of all across all of the possible outcomes with the values weighted by the probability of that outcome. So let's look at an example. Targeted marketing. Evil, but very frequent one. If you gonna work at a company, all companies do that. Some companies who just do marketing do more of that, but still easy to explain and very pretty much real world example. So say a consumer buys the product for $200 and our product related costs are $100. This 100 includes manufacturing, delivery, and everything of that kind. So to target the consumer with the offer, we also incur costs. Let's say that we mail some flashy marketing materials and the overall costs including postage is $1, yielding a value profit of $99. Which is 200 minus 100 and minus 1. All of the proceeds minus everything that we spent. But we will get this $99 only if the consumer responds, that is, buys the product. Now, what about the value of the negative outcome, non-responders? If we send our marketing material but the consumer doesn't respond, the value to us is negative $1 because we still made the marketing materials and incurred a cost of $1. Or which is more convenient to think about it as a benefit of minus $1 or negative benefit. So, shall we target this specific consumer? How do we know? This is how we can use the model that predicts probabilities based on the expected value framework. So, probability of responding times the value, $99, minus probability of not responding, 1 minus probability of responding in this case, times the dollar that we spent to send marketing materials and to prepare them, must be greater than 0. If it's greater than 0, then it's worth doing because we are making money. If we rearrange the inequality and solve it, we see that if the probability of responding is greater than 1%, we need to send marketing materials. Look how low the probability of response is. But in our case, the cost of acquiring a customer, $1 practically, is so low that even if probability of this customer responding is just 1%, we're making money. But this is how we could use expected value framework in order to use a model that has been already trained and it's predicting based on features from a customer, it's predicting what is the probability of responding or not. But can we use the same framework for choosing one model over another? So, turns out we can, and we will see now how. First, we will convert confusion matrix to probabilities. Assume we've trained a classifier that produces this confusion matrix on 110 test samples. So let's normalize the counts. Those are the counts. How many out of those 110 were predicted as positives when they were indeed positives? How many? 7 were predicted as positives when they were negatives. So when we normalize everything by 110, and if I was in a class with you, I would pause here and ask you, what is this? What are we getting? What is this object is called? And you would, of course, after hesitating, respond that this is the joint probability distribution of predicted and actual. We will get this joint probability distribution after this process. Now we need to estimate the cost and benefits matrix. So the cost and benefit matrix looks like that. Benefits is something that we gained when we made a correct prediction, and costs is something that we incur when we make an incorrect prediction. But in fact, mathematically and even for reasoning convenience, it's better to call both of them benefits, and just when we plug in the numbers, the benefits in those quadrants will always be negative. So negative benefits or positive benefits. So if we are here in our example, that is, we've sent our materials, marketing materials, and the customer responded and bought the product. Then this is true positive. And how much do we get here? We will get $99 of the benefits. If we are here when we sent something but the customer did not respond, didn't buy our product, then we incur the cost of negative $1. But what if we correctly said, don't send, the customer won't respond? Well, we didn't send, we didn't lose anything, we didn't gain anything, so it's 0. The same case is when we said don't send, they won't respond, but they would have responded. But anyways, even then we didn't incur any costs, it's still 0, and our cost benefit matrix will look like that when we plug in the numbers. The overall process looks like that, the following diagram. Basically, we take our data set, we take train, test, split, we train an algorithm, get a model, use the test split to compute the numbers and evaluate the model on this confusion, to create this confusion matrix. Then we normalize and get our joint distribution here in this matrix. Then we take cost benefit information and then element-wise multiply and integrate. That's how we get the expected value. So if that is the process, what will be the profit in our example? Just writing out numerically or mathematically, symbolically actually, what I just said. We multiply each benefit, the negative benefit and the positive benefit, with probability of that event, or the probability we already computed. But before we compute this numerically, let's use the chain rule of probability that will make some things clearer at least, and we will come back to it in the next sections of this lecture. Let's factor probability, each of them, of the joint probability of prediction and the actual truth as conditional and the prior. So as you see, I did that for each of those probabilities. Then observe that probability of responders or positive is present in those two terms, and probability of non-respondents is present in those two terms. I took it out, and now observe an interesting relation that we have those two quantities, 1 and 2, that are weighted by class probability, or responders and non-respondents. We also observe that those conditionals are actually true positive rate, false positive rate, false negatives is when it's positive, but we predict a negative. And then true negative rate and false negative rate. I said it in reverse. This is true negative, and this is false positive. False positive, false negative, true negative, true positive. Those are the rates and probabilities, class probabilities. So if classes have different size, then we're just weighting those two expressions by the corresponding size of the classes. So in our case, we had 110 test examples, and probability, the responders, number of responders was 61, and number of non-responders was 49. This is just coming from the original confusion matrix. 56, 7, 5, 42. If I sum everything up together, I get 110. If I sum just the positive, 56 plus 5, I get probability of responders. If I sum just the negative, I get probability, or number of non-responders, sorry. And then from here, I can compute probability of responders, 61 1/10, and probability of non-responders, basically 45. And then my true positive rate will be 56 divided by 61. True positive, the number of true positive as a fraction of all positive, which is 92. And then false positive rate it is again the fraction of predicted as positive among all of the negatives, 14%. And then false negative rate, 5, predicted as negative when they were in fact positive, is 8%. And true negative rate, those that were negative and predicted as negative, so now we have everything to plug in and solve for expected value. Let's first plug in our probabilities and leave the benefits aside, the probabilities that we have just computed. Then let's plug in the benefits. The benefit of true positive is $99, and the benefit of true negative is negative. Wait, the false positive. See, even I'm making a mistake here. The benefit of false mistakes. So be careful when you work with it. What you call what and how you treat it, especially. So expected value of a single customer, if we use this model, is $50. So if we send it to lots of customers, on average, we expect from each of them a $50 outcome. Nice, right? So that's it for expected value. But don't yet get too excited that you always need to use expected value and you will always be good, because you can't. Okay. The reason is that this matrix is extremely hard to obtain. In practice, in real production, in real life situations, it's very hard not only to guess those precise numbers, but it's very hard to guess even ranges. But if you can, to work with the domain expert or become a domain expert to make estimates, then having this framework is a very nice benefit.